This is SpaceTime Series 27, Episode 146, for broadcast on the 4th of December 2024. Coming up on SpaceTime, how a nearby supernova could end the search for dark matter, magnetic tornadoes stirring up the haze at Jupiter's poles, and the world's biggest digital camera arrives at NASA's Goddard. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers are waiting for a nearby supernova that could finally end the search for the universe's mysterious dark matter. The nature of dark matter has eluded astronomers for more than 90 years, ever since the realization that 85% of all the matter in the universe wasn't visible through our telescopes. The most likely dark matter candidate today are tiny subatomic particles, hypothetical particles, known as Axions. And researchers around the world are desperately trying to find them. Now, a new report in the journal Physical Review Letters argues that these axions could be discovered within seconds of the detection of gamma rays from a nearby supernova explosion. You see, according to the theory, axions, if they exist, would be produced in copious quantities during the first 10 seconds following a core collapse supernova explosion involving a massive star turning into a neutron star. And those axions would then escape, but be transformed into high-energy gamma rays by the star's intense magnetic field. Such a detection is possible today only if the lone gamma-ray space telescope in orbit above the Earth right now, that's the Fermi gamma-ray space telescope, is pointing in the right direction when the supernova happens. Now, given the telescope's field of view, that's about a 1 in 10 chance. Yet a single detection of gamma rays would be enough to pinpoint the mass of the axion, and in particular the so-called QCD axion, thereby eliminating a huge range of theoretical masses, including mass ranges now being scoured in experiments on Earth. On the other hand, the lack of a detection would eliminate a large range of potential masses for the axion, in the process making most current dark matter searches irrelevant. The problem is that for gamma rays to be bright enough to be detected, the supernova would need to be really close by. That means within our own Milky Way galaxy or one of its nearby satellite galaxies. And stars there only explode on average once every few decades. In fact, the last time one of these nearby supernovae happened was 1987A in the Large Magellanic Cloud. Amazingly, at that time, the now defunct gamma-ray telescope, the Solar Maximum mission, was pointing in the supernova's direction. But it wasn't sensitive enough to be able to detect the predicted intensity of those gamma rays. The study's lead author, Benjamin Safdie from the University of California, Berkeley, says that if we were to see a supernova like 1987A with a modern gamma-ray telescope, we should be able to detect or rule out this QCD axion across much of its parameter space. And all that would happen within the first 10 seconds. Problem is, astronomers are really nervous because when this long overdue supernova does pop off in the nearby universe, they won't be ready to see any gamma rays produced by axions. So scientists are now talking with colleagues who build gamma ray telescopes to judge the feasibility of launching one, or really a fleet of such telescopes, to cover 100% of the sky 24/7, thereby being assured of catching any gamma ray burst. They've even proposed a name for their full-sky gamma-ray satellite constellation, the Galactic Axion Instrument for Supernova, or GALAXs for short. Safdie says all of his team members on this project are pretty stressed out because there's always the chance of there being the next supernova before they have the right instrumentation to study it. And it would be a real shame if a supernova went off tomorrow and they missed the opportunity to detect the axions because there might not be another one for another 50 years. Searches for dark matter originally focused on faint, massive, compact halo objects, or machos, theoretically sprinkled throughout our universe and the cosmos. But when that didn't materialize, physicists began to look for elementary subatomic particles, which theoretically are all around us and should be detectable in Earth-bound laboratories. But these so-called weakly interacting massive objects, or WIMPs, also failed to show up. That's why the current best candidate for dark matter is the axion, a particle that fits nicely within the standard model of particle physics and solves several other outstanding puzzles in physics as well. Axions also fall neatly out of string theory, the hypothesis about the underlying geometry of the universe. and they might even be able to unify gravity, which explains interactions on the cosmic scale through relativity theory and the theory of quantum mechanics, which describes the subatomic universe. The strongest candidate for an axion is a so-called QCD axion, named after the reigning theory on the strong nuclear force quantum chromodynamics. Now, QCD axions would theoretically interact with all matter, though weakly, through the four forces of nature: gravity, electromagnetism, the strong nuclear force which holds atoms together, and the weak nuclear force, which explains the breakup of atoms through processes like radioactive decay. One consequence of all that is that in a strong magnetic field, an axion should occasionally turn into an electromagnetic wave or photon. Now, we should also point out that the axion is distinctly different from another lightweight, weakly interacting particle, the neutrino, which only interacts through gravity and the weak nuclear force and totally ignores the electromagnetic force. Lab experiments employing compact cavities, which are sort of similar to a tuning fork, should resonate and amplify the faint electromagnetic field or photon produced if a low-mass axion transforms in the presence of a strong magnetic field. Now, alternatively, astrophysicists have proposed looking for axions produced inside neutron stars immediately after a core collapse supernova like 1987A. Until now, however, they've focused primarily on detecting gamma rays from these axions' slow transformation into photons in the magnetic fields of galaxies. Safdie and colleagues realised, however, that this process isn't very efficient at producing gamma rays, at least not enough of them to be detected from Earth. So instead, they're exploring the production of gamma rays by axions in the strong magnetic fields around the very star which generates the axions. Supercomputer simulations showed that this process creates a burst of gamma rays that is dependent on the mass of the axion. And this burst should occur simultaneously with a burst of neutrinos from inside the hot neutron star. But the burst of axions only lasts a mere 10 seconds after the neutron star forms. After that, the production rate drops dramatically, and that's hours before the outer layers of the star explode. Neutron stars have a lot of things going for them. They're extremely hot objects. They also host strong magnetic fields. In fact, the strongest magnetic fields in our universe are found around neutron stars known as magnetars, which have magnetic fields tens of billions of times stronger than anything that can be produced in a laboratory. And that would help convert these axions into observable signals. 2 years ago, Safdie and colleagues put the best upper limit on the mass of the QCD axion at around 16 million electron volts, and that's about 32 times less than the mass of an electron. That was based on the cooling rate of neutron stars, which would cool faster if axions were produced alongside neutrinos inside these hot compact bodies. The new study not only describes the production of gamma rays following core collapse of a neutron star, but also uses the non-detection of gamma rays from the 1987A supernova to put the best constraints yet on the massive axion-like particles, which differ from QCD axions in that they don't interact through the strong nuclear force. They predict that a gamma ray detection would allow them to identify the QCD axion's mass if it's above 50 microelectron volts, or about 1/10 billionth the mass of an electron. And it would take just a single detection to refocus existing experiments to confirm the mass of the axion. While a fleet of dedicated gamma-ray telescopes remains the best option for detecting gamma rays from a nearby supernova, a lucky break with Fermi would be even better. Safdie says the best-case scenario for axions is Fermi catching a supernova. It's just that the chances of that occurring are really small. But if Fermi saw it, scientists would be able to measure its mass. They'd be able to measure its interacting strength. They'd be able to determine everything they need to know about the axion. And they'd be incredibly confident in the signal and what it means because there's no ordinary matter which could create such an event. Here's hoping. This is SpaceTime. Still to come, magnetic tornadoes stirring up the haze of Jupiter's poles, and the biggest digital camera ever made arrives at NASA's Goddard Space Flight Center. All that and more still to come on SpaceTime. A new study has shown unusual magnetically driven vortexes at Jupiter's poles which may be generating Earth-sized concentrations of hydrocarbon haze. While Jupiter's great red spot has been a constant feature of the Jovian landscape for centuries now, astronomers have discovered equally large spots at the planet's north and south poles that appear to be seemingly random. These Earth-sized ovals, which are only visible at ultraviolet wavelengths, are embedded in layers of stratospheric haze that cap the planet's poles. The dark ovals, when seen, are almost always located just below the bright auroral zones at each pole, which are akin to Earth's northern and southern lights, the aurora borealis and aurora australis. A report in the journal Nature Astronomy claims that these spots absorb more ultraviolet radiation than the surrounding areas, and that's what's making them appear dark on images from NASA's Hubble Space Telescope. In early images of the gas giant taken by Hubble between 2015 and 2022, a dark ultraviolet radiation oval appeared 75% of the time at the South Pole, while similar dark ovals appeared in 1 in 8 images taken of the North Pole. These ultraviolet ovals are hinting at unusual processes taking place in Jupiter's strong magnetic field, which propagates down to the poles and deeper into the atmosphere, far deeper than the magnetic processes producing aurora on Earth. Dark ultraviolet ovals were first detected by Hubble in the late 1990s at the north and south poles of Jupiter, and subsequently the North Pole by the Cassini spacecraft, which flew by Jupiter in the year 2000, but back then they drew little attention. But when University of California, Berkeley undergraduate Troy Sabota conducted a systematic study of recent images obtained by Hubble, he found they were a common feature at the South Pole, counting 8 southern ultraviolet dark ovals between 1994 and 2022. Most Hubble images had been captured as part of the Outer Planet Atmosphere's Legacy or OPAL project directed by NASA's Goddard Space Flight Center in Greenbelt, Maryland. Using Hubble, OPAL astronomers make yearly observations of Jupiter, Saturn, Uranus and Neptune in order to better understand their atmospheric dynamics and evolution over time. Sabota and colleagues theorized that the dark ovals are likely stirred from above by a vortex created when the planet's magnetic field lines experience friction in 2 very distinct locations. In the ionosphere, where astronomers had previously detected spinning motions using ground-based telescopes, and in the sheet of hot ionized plasma around Jupiter, which is shed by its volcanic moon Io. The vortex spins fastest in the ionosphere, progressively weakening as it reaches each deeper layer. Like a tornado touching down on dusty ground, the deepest extent of the vortex stirs up the hazy atmosphere to create dense spots. Now, it's not clear if the mixing dredges up more haze from below or whether it's actually generating new haze. Based on the observations, the authors suspect that these ovals are formed over the course of roughly a month or so, but they dissipate in just 2 weeks. And the haze in the dark ovals is 50 times thicker than the typical concentration. That suggests it likely forms due to the swirling vortex's dynamics rather than chemical reactions triggered by high-energy particles in the upper atmosphere. The observations also showed that the timing and location of these energetic particles don't correlate with the appearance of the dark ovals. What the findings do show is how atmospheric dynamics in the solar system's biggest planets differs so widely from what we know here on Earth. This is SpaceTime. Still to come, the world's biggest digital camera arrives at NASA Goddard for installation in the Nancy Grace Roman Space Telescope. And later in the Science Report, paleontologists studying dinosaur feces to better understand how they came to dominate the world. All that and more still to come on SpaceTime. The primary instrument for NASA's Nancy Grace Roman Space Telescope has just been delivered to the agency's Goddard Space Flight Center in Greenbelt, Maryland. Called the Wide Field Instrument, it's the largest and most sophisticated camera ever built. It'll survey the cosmos from the outskirts of our solar system all the way out to the edge of the observable universe, some 13.8 billion light-years away. The camera's large field of view, sharp resolution and sensitivity from visible to near-infrared wavelengths will give the Nancy Grace Roman Observatory an unrivaled deep panoramic view of the universe. Scanning much larger portions of the sky than astronomers can with NASA's Hubble Space Telescope, or for that matter with the Webb Space Observatory, it'll open up new avenues of cosmic exploration. See, Roman is designed to study dark energy, that mysterious cosmic force thought to accelerate the expansion of the universe. It'll also study dark matter, that invisible substance which only interacts gravitationally with normal matter. And it will explore exoplanets, worlds beyond our solar system. Now, to achieve these many main goals, the mission will precisely measure hundreds of millions of galaxies, providing a unique dataset for astronomers and the potential for a flood of results on a vast array of science. Roman is one of 2 surplus keyhole spy satellites donated to NASA by the National Reconnaissance Office. The NRO didn't need them anymore because its own technology had moved on, and so because Hubble was based on the same keyhole design but looked out into space rather than down towards the Earth's surface as keyhole does, they were offered to NASA. After Roman launches in May 2027, each of the wide-field instrument's 300 million pixel images will capture a patch of the sky bigger than the apparent size of the full moon. The instrument's large field of view will enable astronomers to undertake research that would otherwise take hundreds of years to complete using other telescopes. By observing from space, Roman's camera will be very sensitive to infrared light from far across the cosmos. This ancient cosmic light will help scientists address some of the biggest cosmic mysteries, such as how the universe evolved to its present state. This report from NASA TV.
The Wide Field Instrument is the heart of the Nancy Grace Roman Space Telescope. It is what allows the Roman Space Telescope to take pictures with the same detail as Hubble, but covering an area 100 times larger. Despite this incredible power, the basic design is the same as telescopes around the world. Light enters through Roman's 2.4-meter aperture and is reflected and focused by the curved main mirror, which is also the largest mirror in the telescope. This light is reflected and focused once more by the secondary mirror. More elements tighten the beam and strip it of stray light rays before it passes through the filter wheel. This wheel has a variety of filters that allow different wavelengths of light to pass through. It spins from one to another depending on what the researcher is looking for. Finally, the focused and filtered light reaches the focal plane, where it creates an image on the detectors. These detectors use the photoelectric effect to convert photons into an electrical signal that is then decoded into an image. In Roman's case, there are 18 detectors, allowing it to create 300 million pixel images of large patches of the sky. The large number of detectors and pixels gives Roman its wide field of view. The size of the mirror and the precision of its optics gives Roman its fine imaging. This combination of image size and detail has never been possible on a space-based telescope before, and will make the Nancy Grace Roman Space Telescope an indispensable tool in the future.
This is SpaceTime. And time now to take another brief look at some of the other stories making news in science this week with a science report. A new study claims the more time spent sitting, reclining or lying down during the day may increase your risk of heart disease and death, even if you're otherwise active. The findings, reported in the journal GALAX, contradicted research published last month, which found little difference between people standing or sitting for the majority of their time at work. The new study found that more than roughly 10.5 hours of sedentary behaviour per day was linked with future heart failure and death from heart attacks, even among people meeting other recommended levels of activity and exercise. The study looked at data from fitness trackers that captured movement over 7 days for 89,530 British people. It then followed up on their heart health for an average of 8 years. The authors found that once sedentary time exceeded 10.6 hours a day, the risk of heart failure and death from a heart attack rose significantly, which they suggest indicates a threshold for these risks. Now, as any ichthyologist will tell you, sharks are the vacuum cleaners of the ocean. They help keep the seas clean by consuming dead and dying animals. Now, a new study has shown that the sharks most affected by fishing are the same ones most needed to maintain healthy oceans. A report in the journal Science warns that big sharks help maintain balance through their eating habits, and their sheer size is enough to scare away prey that could overconsume seagrass and other plant life needed for healthy oceans. Sharks can also help shape and maintain balance from bottom up. That means a variety of sharks in a variety of sizes are needed. Yet their many and diverse contributions are all under threat from overfishing, from climate change, from habitat loss, from energy mining, shipping activities, and more, all of which is caused by people. Over 500 samples of coprolites, that is fossilized dinosaur feces, together with dino vomit, have helped paleontologists determine how dinosaurs came to dominate the world. Their report in the journal Nature analysed dino-digestive material. It created three-dimensional images of their internal structure and compared this with existing data in the fossil record to work out the identity, feeding behaviour and relative size and prevalence of the creatures that produced them. From this, paleontologists were able to create food webs which track the rise of dinosaurs over time. They found that the meat and plant-eating or omnivorous ancestors of early dinosaurs took over from other four-legged beasts and then evolved into the first carnivorous and herbivorous dinosaurs towards the end of the Triassic era. Increased volcanic activity may then have led to more diverse ranges of plants to feed on. That allowed for the emergence of larger and more diverse herbivore species. And this in turn led to the evolution of larger carnivorous dinosaurs from the beginning of the Jurassic period and completed the transition to dinosaur domination. Well, with all the lithium battery fires we're hearing about of late, a bit of good news is that the next generation of safer lithium batteries may well be on their way. With the details, we're joined by technology editor Alex Zaharov-Reutt from techadvice.life.
We do hear about EV and e-scooter, and even in the old days, Nokia phone batteries would more or less explode, but that's because there were fake ones, and the EV ones, and especially the e-scooter ones, they get bounced around, people ride them hard, and with some of the EVs, there are things on the road that can strike the underside of a car and pierce a battery.
There are now rules in a number of hotels. They won't let you park an EV undercover because of the fear of the lithium batteries catching alight.
Look, I read that China, a number of cities in China, had just implemented the same rules. And it is a genuine concern because we have had fires that have happened in an EV that have then burnt a number of cars around them, or in the UK, burnt down an entire car park in one of the airports.
Yes.
So there is battery technology. One of them is called lithium titanate, used by the military and NASA for decades, but it was quite expensive. But this can operate at much colder and hotter temperatures than lithium ion. It cannot have a runaway thermal reaction like lithium ion can, so if it gets damaged, it doesn't just start burning, which is very handy in a military situation. And one of the benefits of this technology is that it can be recharged up to 50,000 times, like for many, many years, like more than one decade, without the memory effect. So normally a laptop battery lasts a good couple of years and then suddenly it's not giving you anywhere near as much battery life as it did before. But with this lithium titanate technology, which is going to be commercialized by Toshiba, they're already working on getting this in the new year into home appliances like those blowers and whippersnippers and those sorts of things. But these batteries will last for a decade or two and will retain the vast majority of their chargeable capacity, will operate in colder and hotter temperatures. And the most important thing of all, they recharge in about 20 minutes. So this is the next generation of battery technology that we've been waiting for. There's a famous saying from William Gibson, the author of Neuromancer, that says the future has already been invented. It just hasn't been widely distributed yet. And this is the case for many things. I mean, ChatGPT version 5 with artificial general intelligence is more or less supposedly working in the labs in OpenAI, but it just hasn't been delivered to the public yet. The iPhone was in prototype form in 2004, 3 years before it came to the public. And at that time, it was more of an iPad size before it was shrunken down. So many of the things we'll take for granted in a few years are already in the labs, are already working, but they're just not ready to be commercialized at scale yet. And these lithium titanate batteries, and there are other competing batteries as well, solid-state type technology batteries that don't have any liquids at all, are all being worked on.
When I was working at the ABC, I did a story on how to store your laptop when you don't use it for a while. And the idea was you'd take your lithium battery pack out and keep that in a dark, dry place away from the laptop. And that way it'll last for ages.
Yeah, well, very hard to do that these days when the batteries are built into devices.
Yes, and that's the problem. What do you do if you have a perfectly good laptop or a perfectly good cell phone, for example, but you can't physically take the battery out of it anymore? Does it become a dangerous time bomb ticking, waiting to explode, or are they relatively safe if stored in a dry place?
Generally speaking, they're safe. You're supposed to keep them at sort of 50 to 80% charge. Don't have them stored for a long time at 100%, and definitely do not have them stored at 0 or below because it can stop the battery from being able to be charged whatsoever.
So they are safe, just that if you store them uncharged, they may not charge in the future.
That's correct. So you should make sure that they have at least 50% charge. And look, the danger with modern devices is overcharging. There was a story in the news in the last week or so of a family whose iPad was plugged in, charging normally, and it just exploded. Now, battery technology is generally quite safe, especially in phones and tablets, but you never know what manufacturing defect there is. I mean, there was a manufacturing defect with the Samsung Note 7. It caused every airline in the world to say you're not bringing those on planes. And so we have had battery scares, genuinely big ones, in the past. But if batteries were a real problem, then they'd be exploding all over the place, and that clearly isn't happening. But we are seeing a big jump in these e-scooter and EV battery fires, and that's why various apartment blocks and cities in China and other places are saying, look, have all the EVs you want, but not downstairs. So we are in desperate need of battery technology like this lithium titanate that will not have a runaway explosion if damaged, recharges in 20 minutes, and lasts for a decade, 2 or longer before needing to be replaced. I mean, that is like the holy grail of battery tech. And if you can recharge your battery in 20 minutes, whether it's your phone or a car, to full, suddenly having the battery only last for a few hours or a few hundred kilometers doesn't make any difference because you can recharge it so quickly. And this is the sci-fi tech that we need that we still don't have available at scale, but it is definitely coming. And I think by the end of the decade, there'll be plenty more of these batteries and lithium ion will be slowly phased out.
That's Alex Zaharov-Reutt from techadvice.life. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.